So this is what it actually looks like. Obviously, see multiple, but yeah, it looks completely different. So for me, all of my controls for like for your chat and stuff were probably, or if yours hasn't changed, is still at the top. Like my chat is now called in call messages. Um, my people button, my chat button, um, is all along the bottom right. It's very, very different looking. Okay, change layout. I want it tiled all the time now. I don't want it to auto switch. That should do it, I hope. Okay, so people. Okay, Zena's not here. Teja's not here. Patty's not here. Miriam, nope. And Rimka. Okay, so that's actually accurate for once. Okay, I guess, oh, what I got to do right now is I got to put up the next PowerPoint. So let me, or slide deck. So let me do that on Classroom because it's going to be a new unit. Dynamic studying. Okay, just the mathematical changes. What else could we also be looking at when we look at the changes? Because you're right, we're going to be looking at the math behind this. So this is probably the mathiest of all of the units that we've got. Okay, but the other thing that's actually interesting about this unit, yeah, exactly, are the factors. What causes the population numbers to change over time? Okay, so we have to define a few terms. So if we look at the term population, okay, it's a group of organisms that can interbreed and produce successful offspring living in a certain area. What does that definition also sound like? Yeah. So a population is usually a sample of a species. Okay, so it's a subunit. So a population may include all the members of a species, or it just may include a subset of it. Okay. Population dynamics then are the changes in the number and well, one of the key rules of ecology is to understand why things change over time. Okay. So this is a lake called Crystal Lake in Wisconsin. It's a study lake of University of Wisconsin. My connection's still good. Uh, well, oh, it's fine now. Okay. So in University of Wisconsin, okay, and it's looking at the population of two different groups, the yellow perch and the rainbow smelt, okay, and if you look at this graph, what you'll notice, okay, is a definite change occurred between 1990 and 1995. What was that change? Probably, right? For there were very few rainbow smelt initially coming into the population. Okay, there weren't that many. Suddenly, they just exploded. Okay, and what happened to the yellow perch population is they declined. Okay, probably due to competition between the two species, and probably the rainbow smelt outcompeted the yellow perch and therefore took over the habitat. Okay, so that would be one reason to try and figure out why these changes occurred. Okay, any idea what city this is? Close. It's post Hurricane Katrina. Yeah. So this is New Orleans. Okay. Um, and you can see what Hurricane Katrina basically did to New Orleans, right? So what's the most relevant response to damage to this particular ecosystem, right? And if you look, well, unfortunately, and that would be good, right? These people can't move because they're so poor, right? Most of New Orleans, or remember when Katrina went through, they evacuated the city, right? Um, Actually, I gotta go to the washroom, so I'll be right back. The biggest issue with New Orleans was that there was a huge dichotomy in the response. Okay, parts of New Orleans that are basically repaired now are places like the French Quarter and downtown, but areas that were predominantly poor or black neighborhoods, they're still devastated. A lot of houses have been abandoned. A lot of them are still condemned. It basically shows you the dichotomy in terms of socioeconomic status in places like New Orleans, right? This is another reason why population dynamics is important so that we know how to respond properly. And even then, in this situation, they haven't responded properly. Okay. Okay. Another reason to study population dynamics, okay, um, conservation purposes, right? Um, if we don't know the numbers of a population, how can we protect them? Okay. And then also ideas of resource management and sustainable yield, right? What's interesting about this particular graph? The black line up to 2000, the one that's labeled P, is human population growth. Okay. And you can see the different slopes, right? 100x, 10x, 5x growth, 5 times growth per century. Look at the rate that we use our resources compared to our population growth rate, right? The what is that? Q. So that's G, right? Relative GDP is in green. Uh, F is fishing in pink. E is energy in gigatons of oil. And you can just see how we use resources much more quickly, even than our population increases. Okay. And finally, in order to understand the dynamics of an ecosystem, right? So if you look at this cycle, right? When do these ecological shifts occur? Right? Right now, there's a major ecological shift occurring because of this factor, wood and fossil fuel use, right? Because we're altering amount of carbon dioxide in the atmosphere, and that's going to cause shifts throughout the entire chain. Okay, and then the next question, and we don't know the answer to this one with respect to CO2, is the shift stable, or are we going to hit a tipping point? If we can't keep global temperatures below 2 degrees, which is what the IPCC says we need to do, if we can't do that, what's the new stable point? Or is there a new stable point, or do we turn into a new Venus? Okay, so what do we need to know in order to study populations? Okay, so if you want to study a population, what kind of information do you think we need to know? What will be the first piece of information you think will be relevant? The number of things. Yeah, good answer. Okay, something basically, it's what we call the population size. Um, the page references are to a different textbook, so ignore the page references. In fact, for your textbook, let's see, my Nelson. Log in. What? My Nelson. Took me to the wrong login page. Log in. So population dynamics starts on chapter 12. Chapter 12 starts on page 578. And what we're talking about, characteristics, is on 584. Okay? So we're starting on page 584. Okay. So we need to know the population size. Okay? Which is basically the number of individuals of the same species living within the specific geographic area. Could you get the yeah, I don't know what's going on. Because on my end, everything's moving fine. So let me know when is it? Am I still frozen? Let me put it that way. Okay, so for that I am. So it might be your connection then. Okay. All right. Um, think about your biology class from term one. Well, think about any of your classes in your home school from term one. So when you were in person, okay? Do you know the number of individuals in that class? Like, could you figure out? I'm not saying do you remember it, but would it be possible for you to figure out what the exact number of students in your class was? Yeah. What was it around? I don't need an exact number. Okay. Yeah. So it's going to be around that number. Okay. So population size in a small population like that is relatively easy to figure out because all you have to do is count them. Okay. But let's say I asked you to do the same thing for the number of individuals in your home school, not just your one class, but in the entire school. Would you happen to know the exact accurate number at the end of Sem 1 last year? Okay. Why is it so much harder to figure out? Even, okay. Even admin oftentimes don't know exactly. More classes to visit, more people around. Also, what's the likelihood of everyone in your school in September still being there at the end of January? Yeah, some are going to change schools. Some maybe moved out of Ottawa. Maybe you had new kids move into your neighborhood and had new kids come in. So for a larger population, it's a lot harder. Okay. So how do you think the city of Ottawa gets an accurate get knows what the population is? I mean, there's signs that say Ottawa is over, Metro Ottawa is over 1 million people. How do we know that? Okay, that's one possibility, and then Abby has the other one. Okay, so a lot of times we can't figure out what the actual population size is. Okay, um, and the reason we can't figure out the actual population size is because it's in really large populations. It's really, really difficult to count the number of people living in a particular area. Okay. So if you wanted to know the population of Ottawa, it's a lot harder to figure out. Okay. Now, Vedant mentioned something interesting. He talked about a census. How do we know that the census of the population of Canada is accurate? How do we know that it's not an estimate? No, it's not an estimate. It's an accurate number. So how do we get that compliance? Right. But remember that what happens with the census, I think I chopped mine up, is you get something in the envelope that asks you to go to a particular website and fill it in. Yeah, exactly, Grant. The Canadian census is something you must fill out by law. Okay. There are penalties for not filling in the census form. Okay. The fines are big. There is jail time involved if you don't fill it out. Usually they just have to use gentle persuasion. Um, but but people have to do it. Okay. And it's a punishable felony if you don't. And so you might ask, well, what do you do with homeless people or things like that? You need to get help in filling it out, but you still have to fill it out. Shepherds of Good Hope, whatever. Okay. So that's how they do it for populations of humans. But how the hell do you do it for populations of animals? Right? You can't. I mean, consider your neighborhood. How many dogs are there in your neighborhood? You could probably make a guess, but I bet you don't know for sure exactly. Yeah, probably like 30. It's an estimate. You can't say with certainty that it's 27 dogs, right? So that's one problem with population size. When we're looking at organisms that are not humans, generally speaking, we're talking about population estimates, not population size. Okay. And we'll talk about how we do that in a minute. The other thing that's actually important when it comes to populations, in terms of the characteristics, does the size of a population actually give you any reasonable information? I mean, does knowing that the population of Metro Ottawa is 1 million people actually tell you anything? Ish. No. Okay. So, what would be more useful to know rather than just the number of individuals? Okay. Of the locate density. Okay. And population density is designated by capital D. Okay. And the population density is defined as the number of individuals per unit area or per unit volume. Okay. Per unit area you get, right? Like if we decided what is Metro Ottawa, as Vedant says, you could define that as an area in square kilometers. Okay. Why do I have unit volume up there? No, not high rises. Because remember, this doesn't just apply to people. Aquatic, exactly, Emma. So if you're talking about organisms that live in lakes and oceans and such, well, then we're talking about 3 dimensions, right? X-axis, Y-axis, and Z-axis. So you have to talk about a per unit volume rather than per unit area. Land animals usually live in a flat 2-dimensional surface. Okay, but aquatic animals don't. Okay, the general equation to figure out density is equal to n, the population size, divided by s, the area or volume. This is the first equation you'll need to know because you'll be playing with it. Now, there's no test on it. Okay, as I said, there's no test on this unit, but you should still be comfortable with the equations that you know when to use them when. Yeah, exactly, Abby. That's true. Okay, so if you look at this equation, okay, between n and s, which term is the one that's going to be more difficult to figure out when you're trying to figure out population density? Yeah, it's going to be n because we won't know population size. At best, we can get is a population estimate. Okay, so we can estimate the population size. We're not going to know exactly what the population size is. Volume or area, we can figure out. That we can measure directly. Okay. All right. When we look at populations in general, there are basically 3 ways that populations can be distributed. Okay. Now, I don't remember what species of bird these are. They might be gannets, they might be egrets. Anyways, this is Newfoundland. Okay. And it's a rookery, so it's a nesting site. Okay. What do you notice about in that picture the way all the birds are distributed? Yeah, it's pretty even, right? So the distribution is what we describe as uniform, okay, or even. So the organisms are evenly spaced out in a territory, okay? The reason that this occurs is because the resources that the birds need are evenly spread out, but they are still scarce, okay? So you have competition between individuals, okay? Um, Now, obviously, say, what do you think is the resource that's in short supply in this picture? This is a nesting site. Okay, space. So what determines now, the food is out in the ocean, so they're not feeding off of these rocks. So it is space for nesting. What do you think is going to determine where each bird happens to place its nest on this rock? What determines that distribution? Not social status. Social status would be a more clumped distribution, honestly. So the resource that's in scarcity is space. No, it's due to competition between the individuals. How would two birds compete against each other for the same space? What would they do? Fight. So if they're going to fight, how do birds attack each other? With their beak, right? So how do you think the birds figure out how far apart to put their nests? Not length of beak, because they've got pretty long necks. So length of, yeah, the length of the strike. So each bird will set up just out of reach of the striking distance of the bird next to it. And that sets up this pretty even distribution pattern. Okay, so it's based on neck strike length. Obviously, there's a bit of variation because not every bird has the exact same neck length. There are some with shorter necks and some with longer, but on average, they've all got roughly the same neck length. Okay, which is why you end up with this kind of distribution pattern. Okay, so so this pattern you see here is a negative interaction between individuals, right? But remember, I also said it could also be the result of an artificial situation. Can you think of an artificial situation where individuals are set up equally spaced apart from one another? Human homes is one, but even in that's one. But I was actually thinking, what happens in your classes? How are they set up? How are your desks in your class set up? So is it rows and columns for most of you? Yeah, exactly. So they're set up in rows and columns in a lot of places. My classes were a little weird. I tried this out for it worked for a couple of years. I did 2Us, right? Um, so I didn't have traditional up and down. I just had a great big U, and then I could walk around and I'd teach from the center. I've actually had years where I also made it a complete circle. That didn't work as well because then I had to leave the circle. I could teach from the center, but I had to go out there to hit the blackboard. So that only worked when I was using a projector, right? But if I had to use a blackboard, then I was more likely to use a U shape. More or less, yeah, because I would wander the entire circle. I'd still have kids like put their heads down and sleep. Okay, so it could be artificial, or it could be due to negative interaction between the two individuals. Okay. The second kind of distribution pattern you could have is random. There's no organization. They're just distributed randomly in a territory, no pattern. Resources are evenly distributed, but also plentiful. Interactions are neutral, and you rarely find this kind of distribution pattern in nature. In fact, the only example of it in nature that I could ever even think of, birds on a wire, right? There's lots of space. They're not competing for space, okay? So they've got lots of resources. So they just land wherever. And in fact, some of the birds land facing the other way. This is a random distribution pattern, okay? But yeah, incredibly rare in nature. This is the only example I could think of. I don't know of any other. They can, right? But most organisms, plant or animal, has a distribution pattern that looks more like this, which is called clumped. Okay. Resources are unevenly distributed. Populations gather near them, often common with organisms with positive interactions between individuals. So, for example, think about herds of African prey animals. Zebras stick together. Why? Safety in numbers. Okay. Or You'll have lions that hunt together, right? Higher hunting efficiency, right? What? So yeah, if you look at what Vedant just said, what right? If you look at the locations of the cities in Canada and in the US, what determines where they're located? Not the red lines. The red lines are artificial highways. Okay. What do you think determined the initial position placing of all these cities in North America? Which resource? Yeah, water. These are all by major rivers, because they're all because that's the major source of water for survival, as well as the major transportation system to get goods in and out. Okay, but even in the U.S., they're all pretty much next to major river systems. Okay, so that's what this causes the distribution in North America in general. So what we're seeing, and this is the most common distribution pattern that you're going to see in nature, because for the most part, resources are usually unevenly distributed. Therefore, the population tends to gather around those limited resources. Okay. All right. So how when we talked about this, okay, we said what we need to figure out to do this question is we need to know population size. That's the biggest issue. And in that case, what we need to do is determine population size. Okay. So there's a few ways of doing it. Okay. And your variable changes depending on how you do your sampling. Okay. So if you manage to count every single individual in a population, then the variable you use is S. Okay. So if I was going to use the number of students in my grade 12 bio class from 2 years ago, that was 26 kids. I can count them. Therefore, my population size value is S because I know the exact number. Okay. But generally, for most populations, because of the way they're actually distributed, you have to estimate it. And if you're estimating a population, then you use the term N. Okay. And there are different ways to determine population size. One way is to use something called transect sampling. Okay. Um, when you can't measure S directly, then you have to use N. And the biggest problem in trying to figure out by measuring directly is it's impossible to know if you've counted every individual in the population. Okay. So in a transect sample, uh, yes. So for example, if this is the area you want to measure, you could go to a map, outline the area, and calculate the area that way, right? Because you could basically set up uh, a grid and you can literally measure it. There are computer programs that will allow you to measure oblong or weird shaped structures like this. So you can always do it via Google Earth or things of that nature. That's not that hard to do because obviously we're using Google Earth or something. You've got a scale, and so if you measure it, you can figure it out pretty accurately. So what you do instead is you set up what's called a transect. In a Now, if it's a small enough area, you may only need to set up one transect. So a transect is one of these lines. Okay. And you just lay a line out the and then choose a starting point, one end or the other, and then travel in one direction. And as you go along that line, you just count the number of individuals of the species or population you're interested in that you can see a certain distance from the line. Okay. and you use that to estimate your total population in an area. Now, if it's a larger area like this, you may have to run many transit lines to cover the entire area. And realize this is an estimate because you're only counting the individuals that you can see within a certain distance from that line. If, let's say, you're counting lions and there's a lion that's high sleep taking a nap under a brush somewhere, you won't see him, so you're going to miss him, right? So it is an estimate, okay? So that is one way to do this. I have done this underwater on a West Coast um, rock wall, basically a coral reef. But it's a temperate coral, not like the Great Barrier Reef. So they're very different. Yeah. So I'm in scuba gear. It was it was a 120-foot wall dive. So we had to run one, two. So every 20 feet we ran another transect. So that was basically 6 levels. Uh, we started at the deepest depth and did that the fastest because at 120 feet you can't stay down too long. And we're on these like I don't know if you ever seen James Bond films, but where they're on those mini submarines. So it basically has two props and a big motorized battery powered engine plus two, and then you've got a throttle control like kind of looks like a motorbike that you ride, but it's round instead of wheels. So you just scoot along, and I guess these transects were about 100 to 150 meters long, and you scoot along at about 5 kilometers an 5 kilometers an hour, and we were counting sea anemones on the rock wall. And then at the end of the run, we'd record that, go up 20 feet, do another run in the other direction, then up another 20 feet, do another run in the other direction. So we did that, and Jesus, I must have spent 2 weeks underwater doing that series of transect running. It was a lot of fun, but I got pretty wrinkled because we'd be spending up to what 2 hours underwater, and then you'd have to spend 16 hours on land to blow all the extra nitrogen out of your system so that you wouldn't get bent. So this is one way to determine population size. Another way is something called quadrat sampling. Yeah, when you get air bubbles forming in your skin or in your blood, because you get come up too quickly from depth. So it's like opening up a pop can and you get all those carbon dioxide bubbles. While instead in a human you get nitrogen bubbles, basically depressurizing. And when that happens, it's called the bends because when it initially happened, the bubbles would form and it'd be so painful that people would like in which you get these bubbles in your joints of the vertebrae. It'd be so painful that you would actually be bent over, right? The treatment for that is they have to go into a barometric pressure tank, hyperbaric chamber, and you have to be repressurized so that the gases go back into solution, and then they slowly bring you back up, such that you can just breathe the gases out of your body instead of having them gas out inside of your body. I've been bent once; it's not pleasant. I've had gas bubbles show up in the skin of my arms. I was lucky it didn't show up in my joints. The rate at which you come up, because I get asked that all the time, you should not beat your air bubbles to the surface. So the rise rate for a scuba diver uh, who's doing a non-depressurized, yeah. So you have to come up. So if you're doing a non-depressurized dive, so in other words, you're not going to stop to depressurize at depth, then you want to come up at a rate of about a meter a minute. So if you're at 60 meters, it should take you an hour to get to the surface. The way you know that you're going at about the right rate is you should be going up at the same rate as your air bubbles, which travel at about that rate. Um, Swallow hard. and you pop your ears as you go down, and you swallow hard and pop your ears as you go. It's just same as when you're going up and down in an airplane. Sometimes, and make sure. I mean, and you have to make sure like you don't have colds or anything, because if you're plugged up, if you're stuffed up, you won't be able to clear. And you're right, the pressurized gets too hard high. People have had their eardrums burst under pressure like that. Now, free divers aren't breathing pressurized air, so free divers will not have bend problems. So free divers can go down and back up no problems. Their issue is running out of oxygen more than anything else. But if you're scuba diving, you're on air that's above atmospheric, so it's going to push the gas into your solution, and then that's why you end up getting the bends. Okay. Uh, Now in your textbook, I think has a good example of this quadrat sampling population characteristics. Okay, next page. Okay, in your textbook, if you go to page 588, there is a tutorial or a sample problem on using quadrats to estimate density. So I would take a look at that. So I think I said 588. Yeah, page 588. As it says here. So go see the tutorial on page 588 in your textbook. Okay. So quadrat sampling is really good for small or immobile organisms, things like weeds and grass. So what you're going to do is you're going to use this grid, which is called a quadrat. Okay. And this is a 10 by 10 quadrat. And what you're going to do is you're going to randomly pick some squares. And in each square, you're going to count the number of the population that you're interested in. So one, two, three, maybe four or five different squares. Okay. You're then going to take the average of those four or five squares and extrapolate that number to the area of the entire uh, quadrat box to estimate what the population size will be in here. Then to get an estimate of the entire field, you take that quadrat box frame, you move it somewhere else, drop it, and do another quadrat sample. And you do this four or five times for the area that you're looking at. Yeah, probably, Grant. It's often a really common middle school project. We also do it in grade 9 or 10 science sometimes. And that'll give you the population estimate for something like weeds or things of that nature. Right? Obviously, it has to be small. You couldn't use this on an oak tree. Whoa. Okay. So take a look at that tutorial on 588. That'll walk you through it. It will look, come on, load. So it's basically this sample here. And there's a couple of practice problems if you want to try your hand at those too, just to be sure that you get them. So this talk goes through how to do the calculation, and then these two are practice problems for you to try. So 588, 589. And the answers are at the back, so you can check them yourself. They do. Yeah, absolutely they do, Kirsten. Okay, I'm going to stop there because it's almost 10 o'clock. So we'll take a break, and then I'll talk about the third sampling method, which is called mark recapture. Okay? So let's say what, 10-10? I'll see you then. Okay. So the next method of sampling a population is for more mobile populations, and it's called mark recapture. Okay, in mark recapture, obviously you're capturing something and then releasing it, and then recapturing and doing a sample that way. Okay, so I've done this with trout. So in this particular case, we're using a trap to catch basically fry. They're about yay big in size. Um, if you look at, let's see if I can find it. So the link isn't working. Here we go. Okay. So this is mist netting. Okay. So these are mist nets up here, and I'm not sure what birds they're going for. Uh, cliff swallows. See the birds trapped in the mist nets. It's actually a fairly humane way of tagging birds because the birds aren't harmed, and then you basically release them and ban them. Okay, so that's mist netting. These are just fish traps for trout. And the way these fish traps work is they basically have a V-shaped entryway. So And for whatever reason, fish don't figure out that you can go back out the same way you came back in. So they swim in and that's it. They're basically trapped. They don't turn around and go back out. Okay. The next thing you need to do is you need to mark the animals. Okay. So, yeah, um, I've pit tagged. So pit tagging basically means you anesthetize the fish, you open up their bellies, you put a little radio collar or radio tag, pit tag, into the belly, and then you basically stitch them back up or glue them back up. Okay. If you're bird banding, what you would then do is take just a small metal band and you put it around the leg of the animal after and then you basically release the organism. Okay. So in the case of juvenile fish, you just re-release them into location. Yeah. Uh, Basically in the area that you captured them. Same thing with the starlings or birds. You're going to release them in the area that you caught them. Okay. And in order for this technique to work, there are basically five assumptions. Okay. Assumption number one, chances for the organism to be caught are equal and constant. And you're going to, let me go back one. This whole uh, release, after you release the organism, you're going to wait a certain amount of time and then you're going to trap them again. And when you trap them, what you're looking to see is the ratio between how many organisms have been that you've captured are marked. In other words, you caught previously, and how many are new captures. And it's that ratio you use to estimate the population size. Okay. So in order for this to work, there are five assumptions. The chances that an organism is going to be caught is equal and constant the first time and the second time. In other words, the chance that an individual can be captured is unchanged by the fact that it's been marked. Okay. The proportion of marked to unmarked organisms is constant or the same between captures. In other words, the population hasn't changed. Okay. Enough time has elapsed so that the captured individuals randomly disperse into the population. So it's not that you're capturing more marked ones because you didn't give them enough time to get away. So you have to give them enough time to disperse into the complete population. Um, the marks can't affect the organism, and the organisms can't lose their marks. Okay. So assuming those five things are true, then this is a decent method for figuring out what the population size is. Okay. So how do we do it? So the equation is this: capital M over capital N equals lowercase m over lowercase n. What do these symbols mean? Okay. So after we reset the traps or nets, days or weeks later, usually weeks, okay, we're going to compare the proportion of marked animals to unmarked animals during the second trapping. So M is the total number of marked animals. So if the first time you marked 35 animals, then M will be 35. Okay. N, this is a PowerPoint failure. N is the total population. So N is what you're trying to estimate. Okay. Lowercase m is the total number recaptured. So let's say you marked 35. The second trap, you captured 10. And let's say n is your second sample size. So let's say that you captured a total of 50 individuals. Okay. So that will be how that works. So as an example, okay, you have 20 starlings captured in mist nets. The birds are marked with leg bands and released. A week later, the nets are reset and 50 starlings are captured. Of the 50 birds, 10 were recaptured. They already had leg bands. What's the estimated population size of the starlings? So M is 20, N is total population, lowercase m is 10, lowercase n is 50. So you just plug it into this equation, okay? Rearrange so you're solving for n, which would be capital M times lowercase n divided by m, okay? So when you plug the numbers in, 20 times 50 over 10, and it's 100, okay? So n times m equals capital N times lower n. Isolate the n, you'll get this, plug the numbers in, n equals 100, okay? If you need time to copy that down, I'll leave it up for a minute so that you've got a sample. So if you're unsure of the math, I strongly suggest you copy that down. Do you want me to go back so you can copy out the question? I can only see 9 of you, so you'll have to type in the chat yes or no. Yes? Okay, then let me go back one slide. So there's the question. I'll give you a couple minutes. While you're copying that out, I'm going to get some water. Oh, that's cute. Okay, and the solution then is there. Okay, can I move on? Yeah, okay. Or maybe that's the last slide. Yeah, okay, so that was the last slide. Okay. Stop. All right. The other thing. Yeah, I can probably add it. So create material. I think I have to download it again. Okay, so I need to go back to the VLE. Yeah, I need to grab the next PowerPoint off the VLE. So give me a couple of minutes. Arg, not again. Well, I got to switch browsers for a sec because the system apparently does not like my cache right now. Okay, close, log out. Log out. Okay, so I'll upload that file. Come on, upload. Here we go. File, save as Google Slides. Okay, so I've just posted demography to Classroom as well. So that's what we'll take a look at. Make sure I posted the right one. Yeah, it is. Okay. Okay, there's about 20 minutes left. So we'll at least begin this. All right. So what we're looking at next is something called demography. Okay. And demography really is the statistics of population dynamics. Okay. It's different from the characteristics of population change. It's different from density and all of that stuff because what we're looking at under demography is how the population changes. Okay. So when we look at demography, we're looking at the growth rate, the age structure, and other characteristics of a population. Growth rate, I'm sure you kind of understand what it is. Is the population growing in size, declining in size, or constant in size? What's age structure? What do you think the age structure of a population is? Yeah, it's a population age pyramid. So what it would look like, let's see, that's what's not good. Better yet, a better term would be population pyramid. So if you look at this, so this is from 2016, right? And you can see the various generations, right? Boomers are here, Gen X, Gen Y, Gen Z. Uh, and then I don't know what name have they given to under 14s. Like what's the generation after population Z, right? In that chart, which one are the so-called millennials? Right? Because I'm here, I'm an X Gen. I think they might be the Ys. All right, actually, let's take a look at that. Okay, millennials are 81 to 96. And when was this published? This was published. Okay, it's still saying that this is Generation Z, 97 to present. Okay, it looks like Grant's right. The generation after Z uh, is anyone born after 2010? Generation Alpha. Uh, they haven't really got a defining characteristic yet. Although it's interesting, one of the things that identifies a member of that generation, anyone born after 2010, they're the first group of individuals born who have never lived without social media. Right? There was a time in your life when social media did not exist. Not for anyone born after 2010. Okay, so where's my present? Keep getting lost. Now, when we talk about, come on, present. Thank you. Demography. There are four terms that you need to know. Okay, that's natality, mortality, immigration, and emigration. Because these are the four factors that basically, when they change, will change the size of a population. Okay, so natality is the birth rate. Mortality is the death rate. Immigration, movement of individuals into a population, and emigration, movement of individuals out of a population. Okay, so these are the four terms, for the most part, that control or factor how a population will change over time, the demographics. Okay, one of the other things that we get from uh, data like this is something called a life table. Okay, what a life table does is it basically is a summary of the characteristics, the demographic characteristics of a population. Okay. So how do you figure out what a life table is? For individuals with really, really short lifespans, so insects like spiders, say, which only survive one season, right? 1 year. You're going to pick individuals from a particular cohort, or even let's say fish, right? And you're going to board at the same time, which is what we call a cohort, and monitor how many of them survive until every member of that cohort dies. Okay. So if you look at this life table for this particular grass, okay, here's the age interval in months that they're looking at: 0 to 3, 4 to 6, 7 to 9, 10 to 12 months, up to over 25 months. Okay. The number of individuals alive at the start of the interval. So at age 0, there were 843 individuals. At age 4 months, there were 722. At age 7, 527. Okay. So the number dying during that individual, so between 843 and 722, 121 individuals died. Okay. The age specific mortality rate, what's the rate of death that occurred in this particular age group? The age specific survivorship rate, what's the number of individuals that survived this particular grouping, right? Just double check that. Make sure that I've done that correctly. Yeah, so to get this number, 8.856, you take 722 and you divide it by 843, and that tells you 0.856 individuals survived. On the other hand, if you do 121 divided by 843, then you get 1.1444. So the age-specific mortality rate is calculated by the number of individuals dying in the interval divided by the total number that started the interval. And the age-specific survivorship rate is the total number at the alive in the next interval divided by the total number alive at the first interval. Okay, proportion of cohort alive at the start of the interval, that's just this number divided by this one, right? So 527 of 843 is 0.625. And age-specific fecundity, how many offspring were produced? Or not how many offspring were produced, how many seeds basically were produced, okay, by each individual group, okay? So that's how you do it for small or short-lived organisms, okay? But we don't do that for things like elephants or humans generally, okay? For long-lived organisms, what they tend to do is they follow a few individuals or a cohort for a few years. And in those years, they're going to record the age at which they died. We then extrapolate that over the 40, 50, 60 years um, of the organism's lifespan. Okay. Now, there was one exception to that in humans. Have you guys ever heard of, I think it's a British series called 7 Up? Okay. So this was an interesting BBC series. I think it's BBC. Uh, series called Up. Okay. And I'll show you I'll present the Wikipedia page because it's kind of interesting. So the Up series of documentary films show the lives of 14 British individuals since 1964 when they were 7 years old. The first film was called 7 Up. Later films adjusting a number in the title to match the ages of the subject. There have been 9 episodes, one every 7 years, so 56 years total. Um, so yeah, 7 Up, 7 plus 7 or 14 Up, 21, 28, 35, 42, 49, 56, and 63 Up, right? So they basically followed this is, this will be equivalent to trying to develop a um, life table uh, for British individuals born in 1964. So you're following this cohort for that length of time. Okay. So there's a bunch of them that they followed. So you can see here their participation record, right? Not all of them were involved in every single film. Don't know what happened to Charles. Okay, so looks like one person just had a bit of a falling out. But yeah, this is the basic idea of following a cohort around. Okay. You know, yeah, I guess I can do this too. All right. One of the things that data from life tables can give you is if you graph it, you actually end up with some interesting curves. Okay. And these curves are called survivorship curves. And in a survivorship curve, What it basically tells you is the rate of survival of individuals over the lifespan of the species. Okay? And what you'll notice is that there are basically three basic survivorship curves. Okay? I'm going to do them backwards. Type 3 curves have a really high infant mortality rate. So the individuals, right, the parents, have lots and lots and lots and lots and lots of offspring. But most of them do not make it to adulthood. The majority of them are die. Predation, what have you. Okay, so things like mussels would be one example. What other organisms would follow that kind of life cycle, where you have lots of offspring, but only very few survive to adulthood? Insects follow that kind of lifespan, right? What about in plants? What kind of turtles to a degree? What kind of plants would follow this kind? What would we call plants that follow this kind of life cycle? Yeah, they're the weeds, dandelions, things of that nature. So they have a ton of offspring, but the majority don't survive. But the ones that do make it to adulthood are going to each individually have lots and lots of offspring, but again, with very few survivors. Okay, type 2 survivorship curves, they have a pretty constant death rate throughout their entire lives. So you have a high number of offspring born, but their numbers decline constantly over the lifespan. You basically have an equal chance of dying near the beginning of your life as you do towards the end of your life. The chances of death are pretty even throughout. Okay, squirrels, medium-sized animals, right? Dogs would fall under this kind of lifespan. Right, cats, litters of 6, 7, 8, right? So still a fairly high number, but a lot of them will actually make it into adulthood. Okay, and then you have organisms like us, which are type 1. Okay, the survivorship of our infants is usually pretty high, right? There are very few babies that die if you follow a type 1 survivorship curve. Okay, so everyone has children that, for the most part, survive. Death rate increases towards the end of life. As people reach the maximum lifespan of the on a type 1 curve, that's when numbers of individuals start to decline. Oh God, no. There's lots of them. Coconuts are type 1. Most trees are, a lot of trees are type 1. Elephants are type 1. Giraffes are type 1. Whales are type 1. Right? Dolphins, type 1. Lions, type 1. Cheetahs, type 1, although cheetahs are genetically not that diverse. If they're domestic, yes. Because humans had high. Yes and no. I mean, we've manipulated our environment that we're type 1 now. We were probably type 3 before, or type 2. But back then, we also had far more offspring, right? I mean, think of like Jean Chrétien, the former Prime Minister. He's one of 13, right? Or think of places where economically they're not doing as well. Think of places like Africa, where women in Africa would like smaller families, where they consider 4 to be small. Right now they have families of 6 or 8. Okay, so it kind of depends social economic status as well. They would still be, so like brood X, they're still type 3. Because although thousands emerge, in terms of egg laying, there are millions of them that didn't make it up to through the next stage. All right, it's 10:50. We'll stop it there for now. And continue this tomorrow. I'm going to try and fix my Google Meet by adding a couple of things to it. No homework today, unless other than studying for the genetics test. And if you haven't gotten those biographies done yet, you probably need to work on those. Okay? I think that's it, and probably have a good weekend. I'll spend this weekend making up your genetics test. All right, take care.